So guys, back again with the further regression type analysis. And this stuff is going to be pretty straightforward, I think. We've looked at the situation last lecture, where we saw that there was a linear relationship between two variables. I think was it the cars data we looked at? And we saw there was a linear relationship, and I showed you how to get the regression line and how to use the regression line in making predictions. And that's a very, very important little idea. And surprisingly, guys, actually, here's the why this is important. Let me just give you an insight into why this is important now. Is because machine learning is one of these big this is the very topical, and people are all into machine learning. And one of the basic techniques, if not the most basic technique, is regression analysis. So the stuff we did in the last lecture is what's now known as machine learning, because machine learning sounds a lot better than regression analysis, doesn't it? So if you're into machine learning, okay, you're at a party and someone asks you what you're into, and you say you're into machine learning. Yeah, it's a little bit better than saying you're into regression analysis, right? So, but it's a really basic tool in data analytics regression analysis. So it's very, very important you get on top of it. Okay, so I want to do a little bit more now today and show you that sometimes, though, in practice, things aren't as neat as they were in the first lecture. And so the first thing I want to do is I want to show you that relationships usually are not linear. When you open a data set and you're looking at the relationship between two variables, either there's no relationship between the two variables, so you just get a random splatter of points on your scatter plot when you plot the two variables, or the alternative is that you get some kind of what's called a nonlinear relationship. So you look at the scatter plot and you see that the data is not close to a straight line. So one of the examples that's inbuilt into OR is given by the Indometh data set. Okay, so if I go into the Indometh data set, I see that there's time and concentration. And you've got a subject thing as well. Now, the subject is what's called a categorical variable. We haven't talked about this yet, but we will do. So I want to. So basically, it's just a categorical variable. So it's not a numerical quantity at all. It just tells you. It just labels the subject that the data for time and concentration was obtained. So really, we're not interested in the subject data at the moment. All I'm interested in, I want to plot time against concentration and see what happens. Okay, so. Let me just do that. So I'm going to do the Indometh. It's time. Yes, it is, and cons. So it's time. You have to be careful with the capital letters. Sometimes the variables are capitals, and sometimes they're not. So I want to plot time versus concentration, and the reason why I'm putting time along the x-axis is because it's the first numerical variable that you encounter in the data set. But more importantly as well, if you think about concentration, obviously there's some kind of a chemical reaction going on here, or something. So time happens first, and you're interested in the concentration at a specific time. So usually time goes along the x-axis. It's the independent variable, and whatever else you're measuring goes along the y-axis or the vertical axis, because it's the dependent variable on time. And we're going to be doing that in a little more detail maybe next week. We're looking at something that, if something depends on time, it's called a time series, and there's an awful lot of analysis done on time series, and we're going to be doing that separately. Okay, but in this specific case, I'm going to plot concentration versus time, and this is what I get. Now, guys, I think even the most optimistic engineer would agree that that's not a linear relationship. It's curvy. The relationship is curved. Okay, so it's not a straight line relationship. And that situation then, guys, you are screwed basically, because you don't know definitively what the relationship between two variables is. If it's close to a straight line, you absolutely do. Y is equal to a plus bx. But when it's curvy, you don't. And so then you have a choice. You can walk away because it's not linear, or maybe you could do something else. You could try something else. And basically what people do usually, guys, in this kind of situation is when the curve is nonlinear, is they plot the log of the two variables and see if that gives you a linear relationship. And why does this work? Why am I so smart and I picked on the log to do this? It's because this is what happens in practice. People have been doing this for a long time, independent of data analytics actually, in engineering. So they've been plotting variables one against the other by hand with graph paper. It's pathetic. And finding nonlinear relationships and then saying, oh, I don't want a nonlinear, I want a linear. So what you do in this case, guys, is you get the log of the two variables and see if that's linear. So what I'm going to do now in this case is I'm going to get that. I'm going to get the log of this. Now, this is the natural log. So it's usually called ln, but in R, it's called log. So now what I'm doing is I'm going to plot the log of the time versus the log of the concentration. And when I do that, boys and girls, magically you get a linear relationship between the two. Okay, so I think this is, so that's now this doesn't always happen, but it usually does actually, to be fair. So this is so the log function usually takes a nonlinear relationship and it converts it into a linear, but not always. There's an example in R, in the data sets that are built into R, where that's not true. But I'm not going to go into that because we just get time constraints. We've only got a couple of weeks left. Okay. So, but usually this does work. You plot log of one variable versus log of the other variable, and this is what you get. Okay. So we see that's linear. So what is that linear relationship? Well, now remember now, folks, in this situation here, we want concentration to be the dependent variable. So we want concentration equal to a function of time. So what we're going to do now is we're going to do our LM plot. And when you do the LM calculation, the dependent variable is put first. And the dependent variable is put second after a tilde sign. I know it's just completely random key, but that's what OR wants you to do. So if you do that, so I'm going to get. So when I want to get the straight line that I saw in the log plot, and when I do that, that's what I get. Okay, so you get these two relationships. Okay, so this is important now. So what you have then what this is telling you is that log of time is equal to minus, let me just do it to two decimal places, it doesn't matter. I'm going to do 0.51 minus 1.03. It doesn't matter. I'm just going to do two variables, log time. Okay, so that's what you get. So log time is minus 0.51 minus 1.03 log time. Okay, now that's cool, but not great, because you've got log time and you've got log. This is concentration. I'm sorry, guys. I'm just not a good lecturer. Don't hate me too much. Its concentration is a dependent variable. So you got log of concentration is equal to that. Now, what makes this difficult from a mathematical point of view, guys, is that you've got a log term here, which is fine, and you've got a log time here, which is fine, but you've got this stupid 0.51 thing here. Where is that coming from? How are we going to deal with that? So what I want to do here, guys, is I want to convert minus 0.51 into a log. Now I'm going to press enter here just to get a new line. Okay, so what I want to do is I want to do that. Now, how do you do that? Well, here's the trick. If I get the log of the exponential of minus 0.51, I get minus 0.51, because log and exponential are inverse of each other. Okay, so I can write minus 0.51, which is what I have here, as log of the exponential of minus 0.51. Okay, I can do that. So let me just do that. Will I do that? I'm going to do it. And I can write that as log exp brackets minus 0.51. Okay, so I can do that. That's beautiful. And that's because log and exponential are inverse of each other. So now what is nice now, guys, is that I've got a log concentration. I've got another log term here. But now if you look here, I got a minus 1.03. Oh no, that's not a log. So what you have to remember then from your happy days in secondary school is that if you've got a number outside a log, you can bring that number in as a power. So what I can write this as, I'm going to go down to the next line, guys. And again, this is just, I can write this as plus I'm going to take this here. Now, guys, so what I have here is I've got concentration. Log of concentration is log of exponential 0.51 plus log of time to the power of minus 1.03. I can get the I can calculate what exponential of minus 0.51 is. I'm going to do that here. So I get 0.6 essentially. So what I'm going to do, I'm going to write this one. So if I go back up here, I'm going to rewrite this as, stay with this, guys, it's coming to an end. All right, so I can write this as 0.6. Okay, and again, guys, happy days in secondary school. If I have two logs and I'm adding the two logs, what you do then is you can write that as a single log expression where and that's equal to the log of 0.6 time to the power of minus 1.03. Okay? So log of concentration is log of 0.6 times to the power of minus 1.03. All right, so if you look at now on the left-hand side, I've got log of concentration. On the right-hand side, I have log of the mess inside the log. So therefore, the final thing I can conclude is that concentration is equal to 0.6 T to the power, and let me just call it minus 1. Because that makes it looks nice. Okay. Okay, so that's what the experimental data is telling you. That if you want the concentration at a particular time, then you replace time by whatever the value it is. Now be very careful, guys, and we talked about this before. If you look at the times that this formula is valid for are the lowest time that you got is 0.25, and the largest time I think is 8. Yeah, so this formula is valid for all times between 0.25 and 8. So if I want, for instance, the concentration at T equal to 2.5. So the concentration at T equal to 2.5 is 0.6 star. What is it? I want 2.5. Hat brackets minus 1, and I get 0.24. Okay, so all I've done there is I've replaced T by 2.5 because 2.5 is within the range of the data values that you're given for the time. Remember again, guys, it's between 0.25 and 8. If I get the concentration for time T equal to 10, I can do exactly the same thing. It will be 0.6 times 10 to the power of minus 1. So that would be 0.06, but you're not sure if that's a very good value. It's better than nothing, but you're not that confident of your prediction because 10 is outside the range of the data. All right. So that just gives you an example of nonlinear relationships. The idea, folks, that back here again is that if you go back to this, the original data set that we looked at, or the data set that we looked at, time and concentration, as an engineer, you would suspect that there's a relationship between time and concentration. You know, the more time or the concentration either increases or decreases. In this case, as time progresses, the concentration decreases. So there's some kind of chemical reaction going on. The concentration of the active ingredient that you're interested in is decreasing. That's fine. But you're starting off with the expectation that there is a relationship between time and concentration. That's very, very important. From a philosophical point of view, we're dipping our toes into philosophy here. These days, though, in data analytics, the assumption that there's a relationship between two variables is kind of passé. Like it's not as important as it used to be. These days, you can use OR to investigate relationships between any number of variables, and you're not sure about if there is any relationship between the variables there at all, if that makes sense. So you've got a database and you want to investigate the relationship between the variables. You're not assuming that there is ab initio from the beginning. Okay, so let me just show you. Let's look at what some of the data sets that we have. Okay, yes, the Framingham set. So I'm going to take this one, guys. It's in my directory. It's called the Framingham Heart Study data set. If you type that into Google and search for it, you will find it. I think it's in Kaggle, or it could be in UCI as well, but it's all over the web. It's a very famous study. Okay, so it's a study of people with heart problems or not heart problems in a town, I think it's in Massachusetts, called Framingham, and they recorded all these different variables about all these different patients, and we'll see what they recorded in a second. Okay, so I've already that data set in my working directory, and I called it framingham.csv because it's a CSV file and it's the Framingham Heart Study. But you need to load that into your working directory yourselves. So go on Google, type in Framingham Heart Study dataset and upload it into your working directory. So I'm going to call this Fram because I'm just a genius. Okay, so I'm going to read the dataset into this data frame called Fram. And let's look at the structure of Fram. And there's what you see. Okay, so you see there's 16 variables. And there's 4,240 observations, rows of these 16 variables. And you'll see here, guys, as I said, this is a heart study. So you've got male or female. Male is 1, female is 0. You've got, and that's, I don't know if that's a subconscious bias on the part of the researchers. Shame on them if it is. And then you've got age, that's not a subconscious bias, I don't think. Education, maybe that is subconscious as well. I don't know what the numbers represent. I suspect that 1 represents, I don't know, the lowest. Current smoker, yes or no, and then cigarettes per day, blood pressure medication. You see them. So you look at these variables here, and if you were a medical researcher, then you'd be interested in the relationship between these variables. And we're always told that there is, if you look on the web and you might ask, like BMI is body mass index, and apparently that's a very good indicator of cardiovascular health. Apparently, if you go on the web and type, is BMI related to blood pressure, you'll find an awful lot of studies saying that it is. Okay. Now, before these researchers began, they weren't sure if there was a relationship. So the way that you look at, if you've got a database and you want to investigate now the relationships between the variables, one very, very clever way that R has to visualize the relationships between these different variables is just using the plot function on the data frame. So if I type in just simply plot Fram, and if you wait a while because it's doing an enormous amount of plotting in the background. We're still waiting. There you are. And let's wait a little bit more because we want to get all the little plots. It takes a while because it's doing an awful lot of computation in the background. So that's good. Sorry, guys. I just want to get this. And the reason why this is so nice. Oh, I've got the rainbow of death here. The circular rainbow of death. Hang on, let's wait for a while because I think it might be trying to finish up the plotting for us. So I'll just tell you a story in the meantime. And there was this story about a guy who started off very enthusiastic lecturer, but the time he got to teach this course, he could. Here we go. All right. No, we're still waiting, and now we're finished. All right. Now, this plot function, okay, you might be tutting it as I did there about how slow this is, but there's an awful lot of computation going on here in the background. Okay. Now, in some of the variables we're not going to be talking about really that much because some of them are binary variables like male, female, smoker, non-smoker, that kind of thing. And we won't be investigating those. What we're interested in is the relationship between continuous variables like blood pressure and body mass index. And what I think a very, very useful part of these plots is that you can tell pretty much just by looking at the plots if there's any kind of significant relationship, if there's any structure to the data. So let's go down to the BMI, either column or row. Now I'm going to go to the column here. Look at this. Here's the BMI column. Okay, so if I come up to this one here, this gives me the plot of BMI versus blood pressure, diastolic blood pressure. And this gives me BMI versus systolic blood pressure. And if you look at all the data, if you look at all the plots here, all the continuous ones, for instance, this one over here, this is age versus blood pressure. There doesn't seem to be a relationship, folks. Now that's kind of surprising because they say that as you get older, your blood pressure increases or decreases. I can't remember which one it is. But if you look at this data set here, this study, there doesn't seem to be much of a relationship at all. Okay, which I think is interesting. So what is great thing about data analytics, guys, is that sometimes it dispels any prejudices that you might have about different things. You go into a database thinking that there's one kind of relationship or the relationship should be this way. And in fact, the data says that they're not. Okay, and that's not great. Now, the only situation where there seems to be some structure in the relationship is this one down here. Look, if I can bring it over here. Here you got systolic blood pressure versus diastolic blood pressure, and you would suspect that the relationship is pretty good there, because if your systolic blood pressure is high, your diastolic blood pressure is going to be high. One of them is at the start of the cardiac cycle, one is at the end of the cardiac cycle. And so you would expect that that's the case. But what I'm interested in, guys, I don't know, is this idea just to see how true this stuff is. The BMI versus systolic blood pressure. Let's look at that. Okay. Let's see if there is a relationship. There doesn't seem to be one from the overall plot, but let's see if I can plot this. And I'm going to do BMI because that's your starting position. That would be your independent variable, how heavy you are. As a result of being that heavy, you might have a blood pressure. Now, it doesn't matter which blood pressure we're going to take because we know that. Let's look at the systolic one. And I can't spell it. All right. So if you do this here, I'm going to plot these two variables here. And if I come out of here and I'll see here's what it is. Now, if you're doing this in RStudio, you don't have to toggle between different screens, and that's what makes RStudio pretty good. Especially when you're doing graphics interpretation and visualization. RStudio is the place to be when you're doing visualization of data. But if you look at this data here, guys, there doesn't seem to be that much of a relationship, really, is there? You could imagine a straight line relationship, but you've got a big mass of data in here and you don't know what that is, it's just maybe there isn't. It's just, this looks like pretty random. Now, you could imagine that, okay, there's a kind of a very weak correlation, a line here. And certainly you can do the, you can calculate the linear model if you wanted to. And you could plot you could abline that linear model. You could plot the line. So I'm going to have blood pressure on the right, on the y-axis. And if I toggle back again, this is what I get. So all I've done here, guys, is I've plotted the regression line along with the data. Now, you can convince yourself that that makes sense or not. I don't think that there is a very strong linear relationship or any kind of relationship at all between BMI and blood pressure. And this would be counterintuitive. And it's the reason why it's counterintuitive because you hear about this relationship all the time. People being overweight, obesity being a scourge, and it causes all sorts of problems and cardiovascular problems and all sorts of things. But if you look at this study, there doesn't, okay, there's a kind of a weak relationship. It's kind of saying that if you heavier, your blood pressure is going to be higher, kind of, probably, but we're not sure. Okay, so it's not as clear cut as the propaganda tells you. But maybe this study is an anomaly. It's anomalous. It's not representative of what happens in general. And that's the reason why drug trials and medical science is so difficult. It's because sometimes the data, the evidence that you get is not overwhelmingly convincing. And in this case, I would suggest to you that it's not very convincing that BMI and obesity and heaviness causes high blood pressure. It's not that clear to me. And if you look at this one over here, that's a BMI of 60. I think that's like a walrus. I don't know. Like, that is a very heavy person. That is a person who's significantly overweight. Now, I don't mean to trivialize it, but it is. It's a very, very overweight person, and his blood pressure there is about 170, which is high, but it's you could have that by a BMI of 20. Look, there's guys with a BMI of 20, who have the same blood pressure as the guy with a BMI of almost 60. So it's not a very strong indicator of blood pressure. Okay, it's not a very good predicting variable for blood pressure, in my view, at least this study. Okay, so that's what you can do. So there's all sorts of things that you can do. So as I said, I just wanted to just show you how this is what data regression and data analytics has now become. So instead of starting off with two variables where, because you're an engineer and you have intuition, you suspect there's a relationship between the two, you can use R and data analytics to investigate relationships between variables about which you have no intuition about the relationships. Okay, and that's very nice. Sometimes when you do these plots, you get a nice linear relationship, and you can actually and you can do something with it. That is a valuable piece of information. Okay, so I want to then just do the same thing, actually, guys, just very quickly. You remember we downloaded this data set last time. This is this Wisconsin breast cancer data set. I called it M382cancer.csv. Hopefully you call it something more appropriate. But let me just look at this data. Let me call it CD. Right. Now, if I get the structure of that, you see there's an awful lot of variables there, right? So there's 33 variables. Now, you can't really use the plot function on this data set CD because it's just too big. Because the little thumbnail pictures that you get, they would be just unintelligible. So what you have to do there is you have to subset the data set. So let me just take the first, we say 7 or 8 columns here. And the way I'm going to do this, guys, is I'm going to look at reduced data set. I'm going to look at CD, which is my original data set, and I'm just going to have a comma because I want to isolate variables. Now, you can do this in any number of ways. I'm going to take the first beginning with the radius mean down to, we say, fractal dimension mean. So that's about 7 or 8. So let me go from column 3 to column 10. And if I just make sure that it's done what it's supposed to do, yeah, I'm getting 8 columns now as opposed to 33. Okay, and that means the analysis of the relationships between the variables is so much easier from using the plot function. So if I now plot CDR, again, we have to wait for a bit, and you see that there's some relationships that kind of stand out. Some of them are kind of silly, and if you look at this one here, look, these are kind of non-linear relationships, and they're almost perfectly non-linear relationships. And if you look at the radius mean versus the perimeter mean, look, that's the plot there up here. That's the radius mean, that's the perimeter mean along the x-axis, and the radius mean along the x-axis is perfectly correlated. Okay? So what that's telling you is that they shouldn't have measured the perimeter mean because they knew what the perimeter mean was from the radius mean and use a formula. So there's some redundancy here in their measurements. And that probably cost them money to do that. And you could have been clever and avoided that because there's a relationship between the radius of a circle and its perimeter. Okay, because they were measuring tumors and they measured it in 2D, so they got the perimeter. They imagined it was a circle and they measured its perimeter. Because we know that the perimeter is 2 pi r. So if you know what the radius is, you know what the perimeter is. And what happened here, I think, is that they measured both when they shouldn't have. Like, why, so because they weren't smart enough at the beginning, like we are. We're so smart. But guys, you can now look at and then because we don't know anything about these variables really. But we know that there's some redundancies because there are some things that they shouldn't have measured, but there are some things that maybe might be interesting. Okay, so there's some variables that might be interesting. And if you look at, for instance, the relationship between the compactness mean and the concavity mean. Now, I don't know what compactness and concavity means in this context, what the meaning of those two words is. But if you look at these relationships here, this relationship here, it's almost perfectly linear. Okay, and what this is telling you is that if you know what the concavity mean is, you know what the compactness mean is, because it's almost perfectly linear. Okay, so I can maybe bring that out because and so you use this to kind of give it a feel for where the relationships are. So I know that the compactness mean and the concavity mean is pretty linear. So let me just go back here and just do that. Compactness mean. If I could find that. Again, I'm sorry, guys. I'm kind of lost here. I'm not sure if I've got concavity worst here. Where's the mean? Oh, sorry, guys, because I'm up here. Ha 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 ha. Yeah. So I'm sorry. Sorry, guys. It's too late. So I can look at the compactness mean. I can look at the concavity mean. I can plot them individually. So let me just do that, just for the laugh. And this is the relationship that you get. So this is kind of a blown up version of the thumbnail that you saw in the plot of the whole data set. And you will see that the data is very, very linear. Okay. And in fact, if I wanted to, you can plot that, you can get the correlation there between the two. You can, let me just maybe put the regression line through it. I'm going to have, this is my independent variable. This is my dependent variable, the mean. It doesn't matter, but I'm going to do that. And I'm going to do this, and then I'm going to go to the compactness mean here. So all I'm doing here, guys, now is I'm just doing the regression line. Oh, it didn't plot it for some reason, because that's what OR does sometimes. Sometimes it does its job, sometimes it doesn't. But I'm going to end it here, folks. Hopefully your version of OR is more stable than mine, and it will actually do that. Maybe I made a mistake. I don't think so. Did I? I think that's perfectly, and it should plot that, but it didn't. If I went back, if I did it again now, you would actually get the regression, and you can see what it is. But you can actually get the correlation between all the variables in your reduced CD database by just plotting OR, or by just typing in core. And that gives you all the different ones. Now, we were interested in the concavity mean versus the compactness mean. And we saw there, look, it's concavity mean is here. Sorry, guys. Concavity mean here. And compactness mean here is the correlation is 0.88. And in fact, you see, if you look at the concavity mean versus the concave points mean, the correlationship is even higher. It's very, very close to 1. And this is very, very useful information. Okay, so you've extracted something very, very useful here. You found that there's, if you know the concavity mean, you have a very good idea of what the concave points mean is, and you have a very good idea of what the compactness mean data is. So that might be useful if you're a medical researcher. Now, we don't know, because we don't know the first thing of what these variables represent. But it's extracting information like this from databases is what data analytics is all about. And I just want to illustrate it for you, this kind of idea. And when you're an engineer, folks, they might give you a database and you might do something like this. You might discover relationships between variables that nobody knew existed. And you might be able to save money and you'll be a superstar. And let me just encourage you as well that if you're working in an environment and people want say, is anybody here who knows data analytics? You know as much data analytics as anybody in the universe right now. There's a famous phrase by William Goldman, who was a screenwriter in Hollywood, and he said that nobody knows anything. And that's especially true for data analytics. Nobody knows anything. And doing what we've just done here gives you so much information about what's going on. And you would be looked on as a superstar. You know, people would love you. Okay, so I'm going to finish it here, guys, because actually my wife has called me down for dinner, and so I have to go down. And I'll talk again after dinner and do something else. Okay, guys, thank you.